What specific problem does the meta-level system prompt optimizer, Meta SPO, aim to solve, and why is it significant to focus on system prompts in addition to user prompts?
The meta-level system prompt optimizer, Meta SPO, aims to solve the problem of bilevel system prompt optimization, which focuses on designing system prompts that can effectively generalize across diverse user prompts and tasks. This is significant because system prompts serve as foundational, task-agnostic instructions that can enhance the performance of large language models, LLMs, across multiple domains, unlike user prompts that are typically task-specific. By optimizing system prompts, Meta SPO addresses the limitations of existing methods that primarily focus on user prompts, which often struggle with generalization and require re-optimization for each new task. The ability to create a robust behavioral framework through optimized system prompts allows LLMs to adapt more effectively to unseen user prompts, thereby improving overall performance and efficiency. Thus, focusing on system prompts not only enhances the synergy with user prompts, but also establishes a more versatile and scalable approach to prompt optimization.
How does the Meta SPO framework work? Please illustrate the methodology step by step, including the roles of the inner and outer optimization loops.
The meta-level system prompt optimizer, Meta SPO, framework operates through a structured methodology involving two optimization loops, the inner loop and the outer loop. In the inner loop, the focus is on optimizing user prompts for specific tasks. This involves measuring the performance of the current user prompt on examples from the target task, identifying incorrect responses, conducting failure analysis, and generating refined candidate user prompts. The best performing user prompts are then selected based on their effectiveness in addressing the identified issues. Conversely, the outer loop aims to optimize the system prompt across a distribution of tasks. It begins by evaluating the performance of the system prompt in conjunction with the optimized user prompts, aggregating incorrect responses across tasks. Similar to the inner loop, it analyzes these incorrect responses to generate multiple candidate system prompts, which are then evaluated for their performance across all tasks. The top-performing system prompts are selected based on their ability to generalize and synergize with the optimized user prompts. This iterative process allows the system prompt to learn generalizable knowledge over task distributions while adapting to task-specific user prompts, ultimately enhancing the overall performance of the LLM across diverse tasks and domains.
Can you provide a simple illustrative example that demonstrates the inner workings of the Meta SPO algorithm, explaining the optimization processes for system and user prompts?
The meta-level system prompt optimizer, Meta SPO, operates through two main optimization loops, the inner loop and the outer loop. In the inner loop, the algorithm focuses on optimizing user prompts for specific tasks. For instance, it evaluates the performance of a current user prompt on a target task, identifies incorrect responses, and conducts a failure analysis to generate refined candidate user prompts. Once the user prompts converge, the outer loop then optimizes the system prompt by aggregating incorrect responses across multiple tasks and generating new candidate system prompts, which are evaluated for their performance across the distribution of tasks. This iterative process allows the system prompt to generalize effectively, while synergizing with the optimized user prompts, ultimately enhancing the overall performance of the LLM across diverse tasks.
What are the theoretical or practical benefits of using the Meta SPO method compared to traditional prompt optimization techniques?
The meta-level system prompt optimizer, Meta SPO, offers several theoretical and practical benefits over traditional prompt optimization techniques. Firstly, it addresses the gap in optimizing system prompts, which are crucial for generalizing across diverse tasks, whereas traditional methods primarily focus on user prompts, limiting their effectiveness in unseen contexts. Secondly, Meta SPO employs a bilevel optimization framework that allows for simultaneous optimization of system and user prompts, enhancing their synergistic relationship and improving overall performance. Additionally, the meta-learning approach enables rapid adaptation to new tasks with minimal training, making it superior in handling unseen prompts and tasks compared to conventional methods. Finally, Meta SPO demonstrates greater efficiency, achieving high performance with significantly fewer optimization iterations and less data, which is particularly advantageous in resource-constrained environments.
How was the effectiveness of Meta SPO validated in the experiments? Describe the datasets used, metrics for performance, and the significance of the results achieved.
The effectiveness of Meta SPO is validated through extensive experiments across 14 unseen tasks spanning 5 diverse domains, including medical, review analysis, reasoning, grounding, and safety. The evaluation is conducted in 2 scenarios: unseen generalization, where the optimized system prompt is applied directly to test time queries without further user prompt optimization, and test time adaptation, where user prompts are optimized using a few examples from the target tasks while keeping the system prompt fixed. Performance metrics include accuracy and F1 score, which assess the quality of model outputs against ground truth responses. The results demonstrate that Meta SPO consistently outperforms baseline methods, with 85% of user prompts showing improved performance, indicating strong generalization capabilities and efficient adaptation across diverse tasks. Additionally, the system prompt optimized by Meta SPO exhibits robustness even in low similarity scenarios, underscoring its practical applicability in real-world settings.
What limitations does the proposed method have, and what potential improvements could be made in future work based on the findings presented in your paper?
The proposed meta-level system prompt optimizer, Meta SPO, has limitations primarily related to its reliance on the quality and diversity of source tasks used during meta-learning. While the framework demonstrates strong generalization capabilities, its performance can be enhanced by incorporating a broader range of source tasks that closely resemble the target tasks, as indicated by the positive correlation between task similarity and performance improvement. Additionally, the current implementation may benefit from further exploration of different prompt optimization techniques beyond those already integrated, as the results suggest that variations like Meta SPO with APE and Meta SPO with EVO yield substantial performance gains. Future work could also investigate the optimization of system prompts in more complex, multimodal scenarios or with additional constraints to further enhance adaptability and robustness. Lastly, exploring the integration of user feedback during the optimization process could lead to more tailored and effective system prompts.